Yeah, my name is Raphael, and it's an honor today to introduce Amit Jain and Harika Gaggara. And they'll be talking about automation of machine learning lifecycle for manufacturing. So Amit Jain is an accomplished hands-on technology leader and strives to build products that solve business problems with technology. He has 16 plus years of industry experience in software engineering, cloud computing, machine learning, and product management. He enjoys taking research to production and has pivoted his career into building end-to-end production-grade machine learning solutions. Harika is a data scientist with 4 plus years of experience, currently working at Acerta Analytics. She's a graduate from University of Toronto and specializes in machine learning. She enjoys hiking and photography and doing photography in a without much ado, I leave the floor to Harika and Emmett.
Thank you, Tavo. Welcome, everyone. Thanks for spending your time with us. We will begin now. Let me share. All right. So, the title of our talk is MLOps at Acerta, automation of the ML lifecycle, for specifically for the manufacturing use case. So, this, sorry for this. Yeah. So, this is the agenda. What we have, we want to introduce ourselves, our company, Acerta. Um, how the machine learning system was initially built, how we kind of used MLOps practices and built the next generation of machine learning system, and then what is the future work which we're planning to do. So, yeah, this is a very quick introduction on both of us. So, I'm the director of machine learning with Acerta, overall 16 plus years of experience. I love to mentor people, new folks who are coming into data science industry or to Canada. I'm a parent, father of 3 kids. Most of my time goes with my kids. I love networking and I'm a complete outdoor person. We have Harika with us, who's um, with around 4 years of experience, and she's a great machine learning engineer and a data scientist. She's a huge fan of Friends. Maybe play some Friends trivia with her sometime. She enjoys hiking, cooking, and photography, which is now good because we have good weather outside. All right. So now Acerta. So Acerta is a cloud native platform specifically designed for automotive manufacturing. So the company was founded out of University of Waterloo in 2017. So we are pretty new. We got our Series A funding last year, um, and what we have is basically two platforms. We have a line pulse and we have an auto pulse. So line pulse is primarily for the manufacturing line. So if you see, we have a production assembly line here, and we want to use machine learning uh, to improve efficiency to of the plants. I'll cover line pulse in more detail later. And then we have auto pulse, which is kind of predictive maintenance of automotive uh, automotive vehicles on the road. So let's say any doing a predictive analysis when maybe this brake will wear off or stuff like that. This is the whole suite of line pulse components which we have. We offer a lot of value to the manufacturing clients. Uh, we have database as a service. We expose their data in a very user friendly manner. We have um, these things like smart light analytics, which will be our focus of the talk today, capability metrics, drift detection, all these kind of giving information on how these signals are flowing on the manufacturing line. So a signal is, let's say, a voltage or a pressure of some equipment, and then based on the demand we can have anomaly detection, like if this part which is being manufactured has some defect, we can have drift detection on multivariate signals and lots of things. And we have two deployment options. We can deploy as a Docker container on the station, which is on the user side, or we can have a pure SaaS platform. The use cases are a couple of use cases here. We have axles which are manufactured by the OEMs. Um, we with our machine learning models, we have been able to improve the efficiency and reduce the failure rate uh, and rework. So 65% of gains in that. Gearboxes, the warranties were reduced by 40%. Transmissions, we did a root cause analysis, basically which features or components are causing trouble, so we can improve on that. That caused a significant boost. um, and now autopulse. Autopulse is kind of machine learning live on the field when the cars are running. So we had one success use case where the engine was supposed to fail on a car, and our model predicted the engine failure 400 kilometers in advance. So this can be a lifesaver if you are, let's say, in a cold weather and you're going out somewhere and you get to know this earlier. You don't want to get stuck in a snowstorm or something like that. So this is um, the two suites we have: line pulse and auto pulse. Now I want to shift our focus to a particular application on the line pulse, which is the smart line analytics. What it basically does is when the components are getting manufactured on an assembly line, it does what we call as a root cause analysis. What it means is, if this component, let's say an axle is getting manufactured, so it starts from start to end and an assembly line. Um, this component at the end of line testing, which is the manufacturing terminology, we can predict whether this is a failure or a pass. And if this component is a failure, we can trace it back to which features or which signals or which components can have probable issues. What is the probability of these components failing? And then we can give inputs to the plant managers that let's say station A or maybe point A is where you should look at for defects, and rather than throwing this the entire component, you can go back and fix this particular path in your assembly line, and then it improves the efficiency. So you, rather than throwing the work out or the throwing the complete excel out, you can just change or tweak the components in midstream. So this is the initial um, machine learning model which we had. So on the left we have the transform data. So we basically do some transformations and store the data here. And then we had one single Jupyter notebook, which used to do the typical machine learning processes: data extraction, cleaning, pre-processing, training, and predictions. And it used to store in the database, and the client can, this client is, it can be a UI client, basically a graphical user interface for the plant managers, and they can see the charts. And then we had logging and tracking of experiments with MLflow. And we have a couple of assembly lines which are anonymized to just prevent the privacy and confidentiality for clients. But this is the legacy system where when we want to deploy, we used to do a manual execution of a make file, and it used to sequentially run line one with its parameters. It can be date, it can be what type of operation it is doing, it is what type of things it is manufacturing. Run through this code, this Jupyter notebook runs, stores this result for this line. Then this is a sequential execution, so this runs, then this runs, then this runs, right? So I don't want to spend a lot of time on this. I just want to highlight the issues which are there, and what made us to switch to the new platform. Um, so there are a lot of problems with the legacy system, but I want to emphasize that this is a typical startup problem, that we don't want to worry about optimizations first. We want to worry about product fit and solving the problem. So this is what we did. We solved the problem for manufacturers, but now we faced issues when we want to scale the system, because this is kind of a sequential execution, and the code is kind of in a one Jupyter notebook, so we really can't take it to uh, 10 of hundreds of customers, right? So and the other thing is on the so on the scalability part, right, the code was not structured in a proper manner. We were not using the try principle, which means don't repeat yourself. So we were copying code here and there rather than creating classes and doing inheritance. um, we were not able to do reproducibility with this existing the legacy system, because we were not tracking any metadata. We were not able to trace our experiments end to end. What I mean by end to end is right from which date I ran the experiment, what models were used, what pre-processing was used, what were the graphs which are generated, and what was the version control of the data, the model, the code. We couldn't do anything of that sort. The code quality was a big concern for us. We had no CI/CD process. We had no code coverage. Again, this is a, a startup, so we our focus initially was more on getting getting to a working solution. We had a deployment time of more than a week. There was no orchestration. There was a lot of dependencies on uh, different libraries. We didn't have a standard dev environment to say. Uh, and then I can keep going and going, but uh, this is this project of specifically for the smart line analytics. Good thing is we were facing these issues, which means that the product fit is found, manufacturers are using it, and they want more lines, more assembly lines to be brought under Acerta's platform, which is a good thing for us, right? So that is where we thought of, why don't we apply the new principles effectively, which is taking research to production, which is now called MLOps. Um, and that's what I want to discuss next. And I'll ask Harika to pitch in and start from here. Harika, can you take over, please?
Yep, sure. Thanks a lot, Amit, for giving this background information. As you guys saw, like the problems that we discussed, now let's see how we dealt with them, and we bucketized our problems into these buckets and how we tackled each one of them. Can you go to next slide?
Sure.
So containerization. So this seemed to be a low-hanging fruit when we started our project. Many reasons for it. As Amit mentioned, we had like one Jupyter notebook with all the code in it. So first, we broke down our code into multiple components. And if you look at the end-to-end machine learning lifecycle, we have like data ingestion, data validation, feature engineering, training, validation, and so on. So initially, we created these three components: the data ingestion, pre-processing, and training. And when we created this, it kind of made sense, logical sense for us. And also, we were able to connect the building blocks. So we created like separate Docker containers for these three components. And when we created the Docker components, we made sure that each component is independent of each other. I'll let you know like what that means in a minute. And by creating these Docker containers, we didn't have to worry about reproducibility. Why? Because the Docker containers are kind of immutable in nature. And if we want to reproduce the same results like 1 month down the lane or 2 months down the lane, we can just rerun the Docker containers and it gives the same results. And another thing we were able to achieve by doing containerization is parallelism. So if you saw when we saw the legacy system, you saw everything is getting executed in a sequential manner, and it used to take a lot of time to do like time to market, like around 1 week to do the entire deployment process. But when we were able to do everything in parallel, we brought down the execution time by a lot. And also we made a simple Python script for orchestrating our containers. So what I mean by that is, when this Python script runs, first it calls the data ingestion image, and all the lines are run in multiple containers. And once that is done, the pre-processing image will be pulled in, and similarly all the lines will be run in parallel in multiple containers, and similarly for the training. So by executing this in parallel, we brought down the execution time by a lot. So from week, it came down to hour. So can you go to next slide?
Yep.
So once we dealt with that problem, the next biggest thing which we want to deal with is versioning. So when I started out as a data scientist, I used to have like a lot of issues with data drifting, model drifting, and if I want to reproduce the same results like 1 month down the lane, maybe someone in the team would have changed some hyperparameters, or something would have changed, maybe a pre-processing step. But there is no way to track back or backtrace this information and try to reproduce, because we were not tracking the models, or we were not tracking the data which we were using. So we found DVC to do the job for us. So basically, DVC is nothing but data version control. What it does is it versions models, it versions the data set or any intermittent files that we want to. So if you look at the right-hand side on the top, the config file, it's a basic config file for DVC. And one more thing, one more big advantage of using DVC is platform agnostic. So it can connect to any storage unit like S3 buckets, or Azure Blob storage, or even like Google Drives. So for our project, we used S3 buckets. And if you look over there, like the URL which you're seeing is the URL where our data will be stored. So that's the basic config that we made. And DVC works like very similar to Git. So it's just a Git extension. How we do like Git add and Git push. Similarly, we do DVC add the file name and then DVC push that particular file. So when we do this DVC push, that if in case, for example, I'm going to take a pickle file that is generated out of data ingestion. So when we do data ingestion, I'm extracting a pickle file out of the database and I'm storing it locally. And once it's stored locally, I can just do DVC add in the file name, and then a .dvc file will get generated. So what it has is the path for the S3, and it has the metadata information. And once I do the DVC push, the pickle file itself will be stored in S3, and we can track it via Git. So in this way, we were able to achieve model versioning, data versioning, or any intermittent files which we have. And we could achieve traceability by using DVC. Okay, next slide. And another important feature that we've implemented in our project is the metadata store. So this kind of goes hand in hand with a previous feature which I mentioned, the DVC. So if you see here, we have like multiple components like data ingestion, pre-processing, and training. So in data ingestion, if you see, these are the fields that we were tracking via the metadata store. So if you see, we have like the experiment ID, the line targets, it's specific to a client, and the data resource URL. So this data resource URL is the S3 path, which I mentioned in the previous slide. So this S3 path is used in the consequent steps so that we don't have to hit the DB again and again. And also we are using like data validation, what's the start date and end date. In case if you want to reproduce, we can just come over and see like whether the data validation is done or what was the start date and end date for this particular experiment. And the next one is the pre-processing. Similarly, we have like the experiment ID, we have the pre-process resource URL, the pipelines, and the important thing which we're tracking here is the pipeline steps. So let's say when we want to do feature engineering, we have like 10 different steps or scripts we have to generate multiple features. And let's say you want to change a step and repeat the same experiment. And in that way, you don't have to repeat the data ingestion because it's already done. You can save some time and just go ahead with the pre-processing and training. And similarly, coming to the training part, we have same experiment ID, we have the resource URL, and here we're tracking the framework which we're using, AUC score and the hyperparameters. So again, instead of type GVM framework, you want to use like TensorFlow or PyTorch and things like that. We can just repeat the training instead of repeating the pre-processing or data ingestion, and we can just compare the results between multiple experiments or multiple frameworks or even multiple hyperparameters, and just get the results based on that. And one thing which I want to highlight in this slide is the experiment ID. If you see, the experiment ID is same across the multiple components. That's because we are tracking the end-to-end machine learning lifecycle with just one experiment ID. So later, like 2 months down the lane, if Amit wants to come and ask me like, hey, can you repeat this particular experiment for this particular date? I can just extract this experiment ID. I already versioned the data the pre-processing and the model. So I can just repeat this experiment and I can produce the results to him, which is very straightforward. Can we go to next slide? Yeah. So as we saw the building blocks, now let's see how everything gets connected to each other and what exactly is our cloud native architecture. So imagine like someone in our team is making a code change and they just create a request, pull request, and merge to either develop or master through by Bitbucket. And, in Azure DevOps, the CI/CD pipeline will get created and it'll get triggered, and you see this automated pipeline will get triggered, and the first step is the data ingestion. So the data ingestion, the data will be extracted from the database, it will be pickled, saved locally first, and then it will be versioned and stored in blob storage. Once it is stored in blob storage, the S3 path will be located, it will be stored in the metadata store. Now once the data ingestion is complete, the pre-processing will get triggered, and in the pre-processing, the data will be pulled from the metadata store. Basically, the S3 path will be pulled based on the experiment ID, and it will download the data from the blob storage. It will do the pre-processing, basically the feature engineering, and imagine like an X pre-processed or Y pre-process gets generated. Once the files are generated, the files themselves will be pickled, stored locally first, and then versioned and then stored into blob storage. And the S3 path again will be stored into metadata store, which will be used in the training component. Once the training runs, the model gets generated and the results will be stored in metadata store, which will be available to our end customer. So where exactly these images are stored? So we are using Azure Container Registry for that. These images, the Docker images themselves are versioned and stored in Azure Container Registry. And also we are using MLflow for model tracking and storing the parameters like the artifacts, which libraries we are using and things like that. And the minor things, some of the minor things which I want to mention is the Datadog. We are using it to monitor our performances across multiple models, and also if we have like set thresholds for measuring our metrics or monitoring our metrics, and if it goes below a certain threshold, a trigger will be set to rerun the pipeline, or it will even alert respective stakeholders on like this particular model is like running below certain threshold. So you can just see why it's happening. So this is our cloud native architecture. And next slide. Yeah. So this is our release pipeline that we have currently, compared to legacy system where we did not have any release pipeline. So this seemed to be a good start for us. So once the CI/CD pipeline gets triggered and once the results are pushed to staging, we send alerts, and we send the alerts to the respective stakeholders who are involved in the project. And once they approve the changes, then the results will be pushed into production, and once again the alerts will be sent out to them. So in this way, everybody are tagged at every stage. So we have like certain gated structure, and yeah, everybody will get to know what's happening. And this is just a code coverage snapshot. From the start of our project, we had a huge emphasis on the code coverage. So whenever we are trying to write any small modularized code, we used to think whether this can be done unit test, or whether we can do integration test on it and things like that. So we had a huge emphasis on that. And coming to the tech stack, so these are some of the tools which we use for our project. And also one more thing which I want to emphasize over here is we try to stay as much as possible in Azure stack, because yeah, entire organization is under Azure stack. So we used Azure DevOps, Visual Studio Code, and Bitbucket and things like that. So these are some of the tools which helped us to achieve our project.
One thing which I would like to add here is our solution, our emphasis going forward is to create a cloud agnostic infrastructure, which means that we can build the system on Azure and then maybe move to AWS as needed. Right now, we are majority on Azure, but we want to be cloud agnostic to some extent as well. And this is where our future work will also come. Yeah, go ahead, Harika.
Thanks, Amit. So basically, this is our going to be our. I would say currently we are working on some of them, and this will be our focus in the next quarter. So we are trying to move everything into Kubernetes and use Kubeflow pipelines. And also we are planning to use Argo for our orchestration, and our major focus is also going to be on auto retraining. And we plan to integrate feature store into our product.
So
And
just to add on the feature store, so feature store is another concept which is kind of gaining traction in the machine learning world of late, and we already have a feature store kind of built in the organization, uh, and that is kind of separate from our project right now, and we are kind of looking into how we can integrate the feature store. So we don't have to build it from scratch. We already have some part of it. Yeah.
yep. Okay. Last but not the least, it's definitely a team effort. It would Amit and I wouldn't have been here if it was not for these teams. So a huge shout out to the MLE team and other teams at Acerta, and also of course like the open source community. None of us would be here without the help of the open source community. So thanks, guys. That brings us to the end of the presentation. Now we're open to questions.
Yes, folks, please. I mean, you can, if you have any questions, you can type on the chat, and then I'll be able to read them out to Harika and Amit.
Can I stop sharing the screen, or
You can still leave it being shared. It's okay. I mean, if there's no question, there's no question right now, but I can just ask a question. So,
sure.
having worked at Intel, so I see a lot of similarity between what you guys are doing for optimizing the production line for an auto industry, similar to what people do also even in the in creating computer chips on large scale. So how amenable is your technology? From your perspective, to other companies apart from just the auto company that you discussed about today?
So our use case is primarily for the automotive manufacturing clients. We are kind of a niche organization. We are, because each like the semiconductor manufacturing is kind of bit different from the automotive manufacturing, right? Because of the level of signals and the micro operations, right? So we are not kind of looking into that. Our kind of emphasis is primarily on automotive.
Got it. Awesome. Yeah. So there's a lot of questions now coming on the chat. How many models do you have automated end to end? Question from Radha Krishnan.
How many models you have automated? So when you say models, right, is it the machine learning models or it is the project? So the models are just part of the training. They are not part of the entire ecosystem. So, and the way we have designed the model, it's flexible because the training component can have one model, and or it can have tens of thousands of models, doesn't matter, because it is kind of independent component. But as a end-to-end machine learning project, this is kind of the first one which we have done, and second one is in the flight. Yeah.
Do you want me to read the next one, or you got it?
I can read. Maybe I'll take another one from the the last one. So currently it is deployed. This solution is deployed to ACI, Azure Container Instance and Registry, is where we store the model, and we are taking it to Kubernetes. Currently, we are working on that. I think How has a question. We are using DVC instead of MLflow for ops. So we are using MLflow and DVC effectively. So DVC, we want to use data versioning. MLflow does not do data versioning in what I've seen. So we are trying of doing a mix of both. Metadata store. So metadata store, we built our own metadata store. We didn't use any open source tool for that. Um, so Marcus has a question. So the data lake and Spark are primarily on the data engineering side of things. These are not machine learning specific, but we have a data lake and a data warehouse solution, which is where our ETLs kind of work on. So we do have, um, and since the containers are there, so the biggest advantage of having independent containers is we can hook to either S3 or we can do uh, Azure blob storage. So we don't have to worry about which storage to use. Um, I think that those were pretty much the questions which were typed here.
That's true. Yeah.
And sorry guys, I was presenting, so I didn't saw the chat on muting myself.
No
Sorry
problem.
about that.
Not a problem. One final question before we go.
Yeah, sure.
So on your architecture, so in terms of security, how do you, I mean, because I'm going to assume that for you to, if this exists within the software, within the environment of the car manufacturing company, then that's okay. But then when you're now sending the data from the from the company or from the industry to the cloud, I mean, what security infrastructure do you have in place to ensure that, hey, guess what? If I'm taking somebody's data and I'm sending it to the cloud, that there is no way somebody else is going to actually tap into that data, because security then becomes a concern for companies. I mean, let's assume it's a Tesla, etc.
Yeah, that's a great question. So we are taking all the mandatory steps to secure the client's data on in transit as well as when it is stored. So we have, uh, I mean, this is kind of with the SRE team primarily, but as far as I know, we have taken all the necessary steps and protocols, and we get regularly audited on those as well.
That's awesome. That's
Yeah.
awesome. That's
And Radhakrishna has another question. So
yes.
so when we move to Kubernetes, not Kubernetes, currently when we are into Docker version, and when we move to Kubernetes, the solution is cloud agnostic. But generally, what happens is cloud agnostic is a North Star. Achieving that is kind of very, uh, it's a bit tricky sometimes, right? So our focus is to go to a cloud agnostic architecture, keeping in mind the deliverables and the time to market also, right? So that's, I think I'll say, this is not a straight answer to that, but as far as we can go given the time constraints, we're trying to be cloud agnostic.
Awesome. Awesome. Thank you so much, guys. I really appreciate it. And I think definitely the folks also appreciate you.
Yeah, thank you guys. So I can maybe share my screen, or in the last sense. So these are our contact details. You can reach out to me or Harika on LinkedIn. That would be best to connect with us. Feel free to reach out to us if you have any other questions later on as well. We'll be happy to answer them.
Awesome.
All right. Thank you, everyone. Thank you so much. It was
Guys.
nice being here.
Thank you,
See
guys.
you. Bye.
Yeah. Bye-bye.
Bye.